Hello, and welcome to Science Before Bed. Tonight, we drift gently into the quiet structure of the Milky Way galaxy, the wide river of starlight we call home. A place shaped by ancient suns, slow forces, and hidden patterns, far larger than they first appear. From here, the pace begins to soften. The Milky Way is not loud. It does not announce itself. It simply exists, stretching across the sky in a pale, steady arc. Within that arc are regions where motion has nearly stopped. Frozen worlds, locked far from their stars, carry surfaces that have not changed for billions of years. These distant planets and moons lose heat so slowly that time itself seems to settle around them. Their landscapes remain still, preserved under layers of ice and shadow. By studying these frozen environments, astronomers learn how worlds cool, how internal energy fades, and how planetary surfaces evolve when warmth is no longer present. The silence of these places stands in contrast to the restless activity found closer to stars. Here, cold dominates completely. Elsewhere in the galaxy, faint glows drift through darkness. Electric clouds of gas, charged by energetic radiation, emit soft, ghost-like light. These nebulae do not shine brightly, they whisper. Their glow emerges when radiation strips electrons from atoms, creating ionized gas that responds to magnetic fields. As particles move and recombine, light escapes in subtle colors, often invisible to the human eye. These regions appear near hot stars or linger as echoes of ancient explosions. By observing them, astronomers trace magnetic structures that cannot be seen directly. Temperature, density, and hidden flows of energy are written into their faint emissions. Even the weakest light carries information. In some regions, stars are not born alone. 3 stars may emerge together, bound by gravity from the very beginning. These triple systems form when dense clouds fragment and collapse at nearly the same moment. Their movements are complex. Often 2 stars circle closely, while the third travels farther away. Sometimes all 3 follow elongated paths, weaving around a shared center of gravity. These delicate arrangements can remain stable for millions, even billions of years. Their interactions shape everything nearby. Planet formation may be altered, disrupted, or redirected entirely. Some triple systems eventually break apart, sending one star drifting alone into the galaxy. Others remain connected for their entire lives, quietly tracing intricate gravitational patterns through space. Not all planets follow gentle paths. Some move along stretched orbits, traveling from deep cold to intense heat within a single year. When far from their stars, their atmospheres freeze. Ice clouds form, surfaces stiffen under frost. As they swing inward, temperatures rise rapidly, gases expand, entire atmospheres shift and flow in a matter of weeks. These worlds exist in constant transition. Such extreme orbits often arise from close encounters or the influence of distant companions. They reveal how chaotic early systems can become and how dramatically orbital shape can influence climate and stability. Across the galaxy, clouds drift that seem warmer than expected. They are not always near stars. They are not always near explosions. Their warmth comes from radiation that has traveled vast distances, originating from ancient events near the galactic center, or from compact, energetic objects. High-energy photons cross space silently, depositing heat wherever they encounter gas. These warmed clouds act as quiet records of long-past activity. They show that energy does not vanish, it moves, it lingers. Some planets are shaped not by impacts or erosion, but by gravity itself. When worlds orbit close to massive bodies, tidal forces stretch them, pulling them away from perfect symmetry. One side feels a stronger pull, the other less. Over time, the planet elongates. Its interior warms through friction. Volcanoes may awaken, atmospheres may shift. Some become permanently locked, with one side always facing their star, heat pooled on one hemisphere, cold fixed on the other. These distorted worlds show how deeply gravity can sculpt matter. Scattered through the Milky Way are clouds of primordial hydrogen, gas that has remained nearly unchanged since the early universe. While much of the galaxy's material has been processed through stars, these regions preserve simplicity. They are cold, faint, difficult to detect. Yet they feed star-forming regions, linking the present to the distant past. They remind us that traces of the universe's beginning still drift quietly among the stars. Not every massive star ends in brilliance. Some collapse silently, forming dense remnants without a visible explosion. Their outer layers fall inward. Light fades. Astronomers search for what is missing, a star that simply vanishes. These quiet endings reveal how finely balanced stellar lives are, and how small differences decide between fire and silence. Some planetary systems form within groups of stars. Gravitational forces overlap. Disks twist and wobble. Planets must find stability within constant motion. Some are ejected. Some settle. Even chaos, it seems, can produce balance. Near the galactic center, dust spirals in glowing disks. Heated by intense radiation, grains shine in infrared light as they orbit the central black hole. Magnetic fields guide their motion. Structures shift slowly over time. These regions reveal how matter behaves under extreme conditions. Far from the core, filaments stretch through molecular clouds. Long, narrow threads of gas feed star formation along their length. Gravity gathers material into dense nodes. Stars ignite. order emerges from apparent chaos. Some stars spend their lives almost entirely alone. They drift far from clusters, untouched by strong radiation or close encounters. Their evolution proceeds quietly. Their solitude shows how varied stellar environments can be. Ancient stars still exist, preserving the chemistry of the early universe. Their atmospheres contain little beyond hydrogen and helium. They glow faintly, unchanged for billions of years. They are living fossils, quiet witnesses to the galaxy's earliest chapters. Some stars remain barely stable, their internal layers shifting and pulsing. Planets orbiting them experience changing light and heat. These systems reveal how delicate stellar balance can be. Gravity also carves clouds into towering pillars. Radiation erodes softer material, leaving dense columns behind. Inside them, new stars form in shelter. Creation and erosion exist side by side. Some stars display exotic chemistry. Rare elements surface in their atmospheres, formed through unusual processes or ancient cosmic events. Their spectra act as records of rare pathways in stellar evolution. Some planets wear rings vast beyond imagination. Halos of ice and dust stretch farther than Earth's orbit. They shimmer faintly, marking violent, formative periods in young systems. Stellar remnants drift quietly. White dwarfs, neutron stars, black holes. They move through darkness, carrying the memory of what once shone brightly. Some systems host many giant planets crowded together. Their interactions reshape orbits, eject worlds, or settle into fragile balance. Magnetic fields snap and realign, creating arcs of high-energy light. Invisible forces leave visible traces. Jets of material stream from young stars, stretching for light years. They carve paths through clouds, carrying energy outward. And far from starlight, planets form in darkness, cold, dim, quiet. They show that planet formation does not require brilliance, only time. As this slow journey continues, the galaxy remains vast, steady, and unconcerned with attention. Its structures persist, whether observed or not. The pace can soften further now. There is no need to hold on to every detail. The Milky Way can remain as a gentle presence, resting in the background, while thought slows and rest begins to settle. In the Milky Way, there are regions where gas drifts so slowly that change becomes almost imperceptible. These clouds span vast distances, yet their internal motion is minimal. Gravity works patiently within them, drawing material inward over millions of years. Such regions are often the earliest stages of star formation. Before light appears, before heat rises, matter gathers quietly. atoms collide gently. Energy dissipates rather than builds. Astronomers study these calm clouds to understand how structure emerges from stillness. They reveal that starbirth is not sudden. It begins long before ignition, in silence and balance. Some of these clouds are shaped by forces that no longer exist. Shock waves from ancient supernovae passed through them long ago, compressing gas and setting slow processes in motion. Though the explosions have faded, their influence remains embedded in the cloud's structure. In other parts of the galaxy, stars orbit in paths tilted at unusual angles. Their motions suggest past encounters with massive objects or slow distortions caused by the galaxy itself. Over time, these tilted orbits create thickened regions of stars above and below the galactic plane. These populations help astronomers reconstruct the Milky Way's history. They show where smaller galaxies merged, where gravitational tides reshaped stellar paths, and where ancient collisions left lasting marks. Some planets orbit stars that travel through these disturbed regions. Their skies experience subtle changes as their stars move through varying environments of gas and radiation. Over long timescales, even these gentle variations can influence atmospheric chemistry. Not all planetary systems remain intact. In dense regions, passing stars can disturb outer planets, slowly pulling them into new orbits. Some are pushed inward, others are sent outward, drifting farther from their parent stars. A few are released entirely, becoming rogue planets. They move through the galaxy alone, untethered to any sun. Their surfaces cool rapidly, and any remaining atmosphere slowly freezes. Despite their isolation, these planets are not entirely inert. Internal heat may persist for billions of years. Subsurface layers can remain warm, protected beneath thick ice. In certain environments, radiation alters matter without visible disruption. High-energy particles pass through gas clouds, changing chemical bonds and ionizing atoms. These invisible interactions gradually transform the composition of interstellar space. Such processes influence future star formation. They determine how efficiently clouds cool, how quickly they collapse, and what kinds of stars they produce. Some stars are born with far less mass than others. They burn fuel slowly and steadily, shining faintly for trillions of years. These small stars will outlive nearly everything else in the galaxy. Planets around them experience stable conditions for immense spans of time. Temperatures change gradually. Radiation levels remain consistent. These systems provide insight into long-term planetary stability. They suggest that time itself can be a defining factor in how environments evolve. Elsewhere, stars rotate rapidly, flattening slightly at their equators. Their fast spin alters internal mixing, changing how fuel is distributed. This can extend or shorten stellar lifetimes depending on mass and composition. Rotation also affects surrounding disks of gas. Material spreads outward differently, shaping the size and structure of emerging planetary systems. Some disks develop gaps and rings long before planets are fully formed. These patterns reveal interactions between growing worlds and the gas that surrounds them. By observing these structures, astronomers learn how planets influence their environment, even before they are complete. There are regions of the Milky Way where light struggles to escape. Dense clouds absorb and scatter radiation, leaving pockets of near darkness. Within them, temperatures remain low and reactions proceed slowly. These shadowed regions protect delicate molecules that would otherwise be destroyed. Complex organic compounds form here, drifting quietly between stars. Their presence suggests that the building blocks of chemistry are widespread, forming long before planets exist. Some stellar remnants spin with remarkable precision. Neutron stars rotate hundreds of times per second, emitting steady pulses of radiation. Their timing rivals the accuracy of atomic clocks. These objects allow astronomers to test physical laws under extreme conditions. Gravity, density, and magnetism converge in ways impossible to replicate elsewhere. Despite their intensity, these remnants often reside in calm surroundings. Their steady signals pass through vast stretches of empty space. The Milky Way also contains stars moving at extraordinary speeds. Some have been accelerated by close encounters with the central black hole. Others were flung outward during the collapse of binary systems. These fast-moving stars trace elongated paths through the galaxy, carrying information about powerful gravitational interactions. Over time, their trajectories slowly change as they pass through varying regions of mass and energy. In quieter zones, gas settles into thin layers along the galactic plane. Here, rotation remains orderly. Motion aligns. This balance allows large-scale structures to persist for billions of years. Spiral arms are not rigid features. They are patterns, moving through stars and gas like waves. Material enters and exits these regions, compressed briefly before continuing onward. As gas passes through, star formation increases. Light appears, then fades as stars drift away. The arms themselves endure, shaped by gravity and rotation rather than fixed matter. Beyond the visible disk, a faint halo surrounds the galaxy. Sparse stars and ancient remnants occupy this region. Motion here is slow and elongated. These outer populations preserve records of the Milky Way's earliest growth. They show where matter first gathered and how the galaxy expanded over time. Everywhere within this system, change unfolds gradually. Even the most dramatic events leave traces that fade slowly, blending into the background of cosmic time. Nothing here is hurried. Processes unfold across millions and billions of years. The galaxy continues its motion, steady and unbroken. Stars rise and fade, worlds form and drift, and through it all, the Milky Way remains vast, structured, and quietly persistent, carrying its history forward without pause. Far from the bright arms of the galaxy, matter becomes sparse. Stars are fewer here, and interactions are rare. Motion slows as gravity weakens with distance. In these outer regions, objects follow long, gentle orbits that take hundreds of millions of years to complete. Some stars here were once part of the inner galaxy, gradually migrating outward over time. Others arrived during ancient mergers, remnants of smaller galaxies absorbed long ago. The light in these regions is dim and steady. Radiation levels remain low, allowing fragile structures to persist. Dust grains drift without frequent collisions, slowly accumulating layers of ice. Within this quiet environment, chemistry unfolds at a measured pace. Simple molecules combine and separate repeatedly, guided by temperature and radiation. Over vast timescales, complexity emerges without urgency. Some of the galaxy's coldest objects reside here. Brown dwarfs and faint stellar remnants emit little visible light. Their presence is revealed primarily through gravitational influence or infrared emission. Planets may orbit these dim bodies. Their skies are dark, illuminated only by distant starlight. Surface temperatures remain stable, changing little over long periods. In such places, time becomes the dominant factor shaping evolution. Processes that would be negligible elsewhere become significant when given millions of years. Closer to the galactic plane, motion increases. Gas flows along spiral arms, guided by density waves. Material compresses briefly, then relaxes again. This rhythmic motion regulates star formation. Too much compression would exhaust resources. Too little would prevent stars from forming at all. The balance allows the galaxy to sustain activity over billions of years. Some stars form with companions bound in complex systems. Their mutual gravity influences rotation, orbit, and mass transfer. Over time, these interactions can alter stellar lifetimes. In close systems, material may flow from one star to another. This transfer changes surface composition and brightness. It can also trigger sudden increases in energy output. These events add variability to otherwise steady regions of the galaxy. Their effects propagate outward through surrounding gas. There are places where interstellar gas becomes ionized without forming stars. Radiation from distant sources excites atoms, causing them to glow faintly. These regions outline invisible structures shaped by magnetic fields. Magnetism plays a quiet but persistent role throughout the Milky Way. It guides charged particles, influences gas flow, and shapes filaments. Though rarely seen directly, its effects are widespread. Some cosmic rays travel vast distances before interacting with matter. Their paths are curved and redirected by magnetic fields. Over time, they deposit energy across the galaxy. This slow energy transfer contributes to heating and ionization far from any visible source. In dense clouds, gravity eventually overcomes internal pressure. Collapse begins gradually. Temperatures rise slowly as material falls inward. As density increases, regions become opaque to radiation. Energy becomes trapped, accelerating contraction. At the center, a protostar forms. Even then, light does not immediately escape. The young star remains hidden, wrapped in gas and dust. Only after millions of years does it emerge. Planetary systems begin forming during this early stage. Dust grains collide and stick together. Small bodies grow, shaping the structure of the surrounding disk. Some regions of the disk become depleted as material is incorporated into growing worlds. Others remain dense, continuing to feed formation. The outcome depends on local conditions. Temperature, composition, and motion all play a role. Not every disk forms planets efficiently. Some dissipate before large bodies can assemble. Others produce multiple worlds with varied properties. These differences explain the wide diversity observed among planetary systems. In older systems, change continues long after formation. Orbits shift slowly. Stars brighten or dim as they evolve. Planets adjust to these changes. Atmospheres expand or contract. Surfaces cool or warm gradually. Nothing remains static indefinitely. Yet the pace is slow enough to feel steady on human timescales. Some regions of the Milky Way are shaped more by absence than presence. Gaps, voids, and cavities appear where energy once passed through. Supernovae and stellar winds cleared these spaces long ago. Over time, gas flows back in, edges soften, structures fade. Still, traces remain detectable for millions of years. At the galactic center, motion becomes intense. Stars orbit rapidly in strong gravitational fields. Gas clouds stretch and shear as they circle the core. Energy density increases. Radiation intensifies. Processes accelerate. Yet even here, long-term stability emerges from constant motion. The galaxy as a whole maintains equilibrium through countless interactions. No single force dominates everywhere. Balance arises from complexity. Across its vast span, the galaxy continues evolving without urgency. Patterns repeat, structures persist. And as this motion carries on, the galaxy remains a quiet system when viewed from within. Change is real but gradual, powerful but measured. There is no need to follow every detail. The processes continue whether they are observed or not. The Milky Way moves forward, steady and unhurried, its countless components drifting together through time. The spiral arms are not fixed structures. They move as patterns, not as solid objects. Stars drift in and out of them over time. As material enters an arm, density increases briefly. Gas compresses. Dust gathers. This compression is often enough to begin collapse. New stars form, bright and short-lived. They illuminate their surroundings, then fade or explode. When the material leaves the spiral arm, activity declines again. The region becomes quieter. Only longer-lived stars remain. This cycling allows the galaxy to reuse the same material many times. Atoms pass through stars, return to space, and begin again. Each cycle adds new elements. Heavy atoms form deep within stellar cores or during explosive endings. Carbon, oxygen, iron, elements that later become planets, oceans, and rock. These atoms drift for millions of years before joining anything new. They cool, they disperse. Eventually, they may enter another cloud, another collapse, another star. On smaller scales, motion appears chaotic. Gas swirls, magnetic fields twist. But across larger distances, patterns emerge. Flows align. Structures repeat. Filaments stretch through molecular clouds like quiet highways of matter. Material streams along them toward dense knots. Star formation follows these paths. Some filaments fragment evenly. Others remain smooth, forming stars only at their ends. The reason depends on turbulence, temperature, and magnetic support. Nothing forces a single outcome. Each region responds to its own conditions. In between active regions, space is thin. Particles are separated by vast distances. Collisions are rare. Even so, this space is not empty. Radiation passes through. Fields persist. Low-energy photons drift for ages without interruption. Some were emitted before complex life existed on Earth. They still travel. Occasionally, they interact. An atom absorbs energy. A molecule breaks apart. Small events spread across enormous time. Some stars wander far from where they formed. Gravitational interactions slowly alter their paths. Over billions of years, the galaxy becomes mixed. This migration blurs the record of origin. Stars of different ages and compositions share the same region. History becomes layered. Yet traces remain. Chemical signatures reveal birthplace. Motion reveals past interactions. By measuring these details, astronomers reconstruct long-gone structures. Ancient clusters. Absorbed galaxies. The Milky Way has grown this way for most of its existence, quietly, gradually. At its edges, stars orbit slowly in extended halos. Some take more than 1 billion years to complete a single circuit. Their motion is gentle and uninterrupted. These outer stars experience little change. Radiation is weak. Encounters are rare. They preserve early conditions better than most regions. Their compositions reflect ancient chemistry. Their paths remain stable. Closer in, variability increases. Encounters become more frequent. Energy exchange becomes common. Binary systems interact. Clusters dissolve. Orbits shift. Still, the overall structure holds. The disk remains thin. The spiral pattern persists. This persistence is not rigidity. It is balance. The galaxy does not rush toward an end state. It does not seek completion. It simply continues. Processes overlap without conflict. Birth and decay occur side by side. Creation does not erase what came before. Even dramatic events fit into this flow. Supernovae release energy suddenly, but their effects spread slowly. Shock waves weaken. Material cools. New equilibrium forms. Over time, even the brightest remnants fade into background gas. Only subtle differences remain. From within, this evolution feels almost still. Change happens beyond immediate perception. Motion becomes background. The Milky Way exists as a long sequence rather than a moment. Its present state is temporary, but stable. Its future will resemble its past more than it differs. Nothing demands attention. Nothing calls for urgency. The galaxy carries on, layer by layer, cycle by cycle, moving forward without haste. And in that steady motion, there is space for quiet. Light does not fill the galaxy evenly. It thins with distance. It bends around dust and gas. Some regions remain shadowed for long periods. There, radiation arrives softened and delayed. Energy dissipates gently. In these dim environments, fragile molecules survive. Chains grow longer. Structures persist. Water, carbon compounds, and simple organics assemble on dust grains. They remain frozen, protected from disruption. Time allows accumulation. When conditions change, these materials are released. Heating frees them into gas. They spread through the cloud. Such cycles repeat across the galaxy. Cold storage followed by release. Preservation followed by motion. Not every region reaches the same outcome. Some clouds disperse before collapse. Others evolve into star-forming complexes. Variations arise from small differences amplified over time. a slight change in density, a modest shift in temperature. Over millions of years, these differences become significant. Stars that form in low-density environments tend to be smaller. They burn fuel slowly. Their lifetimes stretch into tens of billions of years. These long-lived stars change little over extended periods. Their output remains stable. Their environments settle. Planets around them experience consistent conditions. Temperatures fluctuate minimally. Radiation remains predictable. Elsewhere, massive stars dominate. They form quickly. They evolve rapidly. Their light reshapes entire regions. Gas becomes ionized. Winds push material outward. These stars do not last long. They exhaust fuel within millions of years. Their endings are abrupt. The aftermath spreads heavy elements into surrounding space. These materials cool. They mix. Later generations inherit this enriched matter. Planets become more complex. Chemistry deepens. The galaxy therefore remembers its past through composition. Earlier eras leave signatures in later structures. Nothing is entirely erased. Some stars retain nearly original material. They formed early. They remain chemically simple. Others display layers of enrichment, multiple cycles of processing, multiple histories combined. By observing these differences, long timelines emerge. The Milky Way reveals its age without needing a clock. Movement continues even in the quietest regions. Orbits shift slightly. Alignments change. Small deviations accumulate. Paths diverge. New configurations arise. The scale makes these changes feel imperceptible, but they are constant. At any moment, somewhere in the galaxy, a cloud begins to collapse. A star ignites. A system disperses. None of these events disrupt the whole. They integrate smoothly. The Milky Way remains neither static nor turbulent. It exists in a measured state between extremes, active yet calm. This balance allows complexity to grow without instability. It allows structure without rigidity. It allows time to unfold naturally. There is no central rhythm imposed on all regions. Each follows its own pace. Together they form continuity. The galaxy does not hurry. It does not pause. It moves as it always has. And in that motion, space remains open. Processes remain gentle. Change remains slow. The Milky Way continues, not as a single event, but as a long, quiet unfolding. The Milky Way is not defined by a single structure, but by layers that overlap and drift through one another. Gas settles into arms. Dust gathers in lanes. Stars pass through these regions without disturbing their overall shape. What appears solid from a distance is in reality in constant motion. Spiral arms are not fixed objects, they are patterns created as material moves through regions of slightly higher density. Stars enter these arms, brighten the surrounding gas, then continue onward, leaving the structure unchanged behind them. The arm persists, even as its contents slowly change. Between these arms lie quieter spaces. Here, star formation slows, radiation thins, the background glow of the galaxy becomes more uniform. These regions act as buffers, allowing energy to dissipate and material to cool before being drawn inward again. Above and below the galactic plane, the environment shifts further. The density drops, stars become sparse, orbits grow elongated, carrying objects far from the bright central band. Time stretches in these regions, marked by slow motion and minimal interaction. Some stars spend most of their existence passing through these outer layers. They cross the plane only briefly, then retreat into the halo once more. Their paths preserve information about the galaxy's gravitational shape, revealing mass that cannot be seen directly. Dark matter influences these motions quietly. It does not emit light. It does not interact strongly with gas. Yet its presence shapes every orbit, holding the galaxy together without drawing attention to itself. Without this unseen mass, the Milky Way would slowly come apart. Stars would drift away. Structures would dissolve. Instead, everything remains bound, guided by forces that leave no visible trace. On smaller scales, gravity works with greater intimacy. Within molecular clouds, small imbalances grow. Regions of slightly higher density begin to contract. Heat escapes, collapse accelerates. As material falls inward, rotation increases. Disks form. Jets emerge along magnetic axes. Energy is redirected rather than released explosively. A new star begins its long process of stabilization. Around these forming stars, leftover material flattens into rotating planes. Dust grains collide gently. Some stick together. Over time, these interactions build larger bodies, shaping the foundations of future planetary systems. Not all disks follow the same outcome. Some disperse quickly, others persist for millions of years. The timing determines whether planets form and what kinds of planets emerge. Distance from the star matters. Composition matters. Random encounters matter. The final arrangement reflects both initial conditions and chance interactions layered over time. Farther out, where light weakens, formation slows. Ice dominates. Growth becomes quieter. These outer regions often produce worlds rich in frozen material, shaped more by accumulation than collision. Closer in, heat reshapes matter. Volatile compounds evaporate. Rocky cores dominate. Atmospheres evolve through loss and replenishment, responding continuously to stellar output. As stars age, their influence changes. Radiation levels shift. Winds strengthen or weaken. Planets respond gradually, adjusting climates over long spans rather than sudden transitions. Eventually, stellar balance breaks, fuel depletes, internal structures reorganize, the star expands or contracts, altering the conditions of everything that orbits it. Some planets are lost during these phases, others endure, adapting to new energy distributions. Debris fields form, rings appear, material migrates inward or outward depending on mass and momentum. After the star's active life ends, remnants remain. White dwarfs cool slowly, neutron stars rotate steadily, black holes persist without surface or light. Each continues to influence surrounding space through gravity alone. These remnants drift through the galaxy like anchors of past activity. They mark where stars once lived, even after their visible presence has faded. Over billions of years, such cycles repeat: formation, stability, change, dispersal. No single stage dominates. The galaxy maintains continuity through repetition rather than permanence. Nothing here rushes toward an end. Nothing remains unchanged. The Milky Way exists as a system shaped by gradual transitions, where even dramatic events are absorbed into a larger calm. And through it all, space remains open. Processes continue quietly. Structures evolve without urgency. Across longer spans of time, the galaxy reveals patterns that only emerge through patience. Individual stars appear fixed during a lifetime, yet populations drift, separate, and recombine on scales that dwarf memory. The spiral structure slowly reshapes itself. Arms fade and reform. Gas flows inward, then outward again, guided by pressure, rotation, and gravity working together. At the center, motion becomes tighter. Orbits shorten. Energy concentrates. Here, stars crowd more closely. Radiation intensifies. Magnetic fields twist through dense clouds of ionized gas. Material spirals toward the core, not in a straight fall, but through gradual loss of energy. Dust heats, gas compresses. Occasionally, the central region releases stored energy. Winds push outward, particles accelerate. These events do not disrupt the galaxy. They redistribute energy, shaping the surrounding environment before fading back into stillness. Far from the center, conditions soften. Stellar encounters become rare. Motion smooths. Stars here retain wide, gentle orbits. Their paths change slowly. Interactions are minimal. In these outer regions, the past remains preserved. Chemical signatures persist. Old populations continue their quiet passage. Some stars formed in entirely different systems. They were captured long ago. Their compositions reveal origins beyond the Milky Way. Streams of such stars still move together, stretched across the halo. They trace the remains of ancient mergers. Their alignment persists even after their parent structures vanished. By mapping these motions, the galaxy's history becomes visible. not as a single narrative, but as overlapping traces left by countless events. Energy within the galaxy is never lost. It changes form. Light becomes heat. Motion becomes structure. Radiation absorbed by dust re-emerges at longer wavelengths. Momentum transferred through collisions redirects material. Nothing ends abruptly. Even the most violent events settle into equilibrium. Shock waves slow. Ejected matter cools. Over time, turbulence gives way to order. Patterns emerge. Balance returns. The Milky Way does not resist change. It incorporates it. Each generation of stars forms from the remains of earlier ones. Each system carries memory in its atoms. Iron, carbon, oxygen, and heavier elements move from core to core, era to era. Planets inherit this history without awareness. Their rocks contain records older than their stars. Their atmospheres reflect processes long completed. Some of these worlds remain barren, others evolve complexity. All are shaped by the same underlying cycles. There is no preferred outcome, only variation. The galaxy supports extremes without favoring them. Dense clusters and isolated stars coexist. Violence and calm share the same space. On the largest scales, the Milky Way drifts with its neighbors. Local groups interact slowly. Distances change. Even this motion remains gentle. Collisions, when they occur, unfold over billions of years. Structures interweave rather than shatter. Through all of this, the galaxy maintains continuity, not by remaining the same, but by allowing transformation to proceed without interruption. What exists now is not separate from what came before. It is the result of accumulation, redistribution, and time. The Milky Way continues as a process rather than an object, a system defined by motion that never needs to hurry. Beyond what is immediately visible, the galaxy extends into regions defined more by influence than by light. Gravitational reach surpasses luminous boundaries, holding distant material in slow, obedient motion. The halo stretches outward, thin and quiet. Here, stars move on long, tilted paths. Encounters are rare. Change arrives slowly. Globular clusters pass through this space as compact relics. They contain some of the oldest stars still bound together. Their internal balance has survived since the earliest stages of the galaxy. Within these clusters, stars follow predictable patterns. Crowding limits variation. Evolution proceeds with restraint. Occasionally, interactions alter individual paths. A star may be displaced. Energy redistributes. Yet the cluster persists. Its structure absorbs disruption without losing identity. The halo also holds streams of gas, barely detectable. Cold, diffuse material drifts inward. Over time, it feeds the disk below. This accretion is uneven. Some flows arrive smoothly, others fragment. Each contribution alters composition slightly. New elements mix with old. The galactic medium evolves without announcement. Magnetic fields thread through these regions, faint but extensive. They guide charged particles. They influence collapse and expansion. Though invisible, these fields connect distant zones, allowing energy to travel across scales far larger than individual systems. Cosmic rays move along these pathways. They originate in energetic events, then disperse gradually. Their journey can span millions of years. As they pass through clouds, they trigger subtle reactions. Ionization changes chemistry. Molecules form or break apart. Even in stillness, activity continues. Processes overlap quietly. Across the disk, star formation proceeds in waves rather than bursts. Regions awaken, then rest. Timing differs from place to place. This prevents exhaustion. Resources circulate. Balance is maintained. The galaxy avoids extremes through distribution. Energy spreads. Matter migrates. No region dominates indefinitely. The center does not consume the outskirts. The outskirts do not drift free. Rotation ties everything together. Angular momentum shapes structure. Stability emerges from motion. As the galaxy turns, perspectives shift. Constellations change. Alignments dissolve. Yet the overall form remains recognizable. Patterns persist even as their contents change. The Milky Way is not static. It is steady. Its quiet strength lies in its ability to absorb time without losing coherence. Change unfolds without urgency. Structure survives through flexibility. What appears calm is sustained by countless interactions. What appears empty is filled with influence. Nothing here is isolated. Nothing stands alone. Every orbit contributes. Every exchange matters. And still the motion remains gentle. No signal demands attention. No boundary insists on definition. The galaxy continues, untroubled by observation. Over longer durations, even the idea of distance softens. What seems far becomes connected through gradual exchange. Material drifts. Energy diffuses. The interstellar medium acts as a quiet reservoir. Gas cools. Dust settles. Radiation passes through, leaving faint adjustments behind. Within this medium, chemistry unfolds slowly. Simple atoms combine. Molecules form in shadowed regions, protected from intense light. These compounds are fragile. They persist only where conditions allow. Temperature, density, and shielding determine survival. When stars ignite nearby, balance shifts. Radiation alters bonds. Winds reshape clouds. Some regions disperse. Others compress further. Variation replaces uniformity. Across the disk, this cycle repeats without coordination. No signal synchronizes activity. Local conditions decide outcomes. Time smooths the results. Sharp boundaries fade. Gradients replace edges. On still larger scales, the galaxy responds to its environment. Nearby systems exert influence. Tidal forces stretch outer regions subtly. These interactions leave traces. Warps appear in the disk. Streams elongate. Nothing breaks suddenly. Deformation arrives gradually, absorbed into existing motion. As stars continue their paths, their light carries information outward. Photons travel freely. Some escape entirely. Others encounter dust, scattering and warming it. Energy changes form. The background glow adjusts. This diffuse light fills the galaxy, creating a soft baseline from which brighter sources emerge. It is never completely dark. It is never fully illuminated. The balance between light and shadow defines perception. Structures appear where contrast exists. Absence becomes noticeable only by comparison. Over time, even contrast evolves. Bright regions dim. Quiet areas accumulate faint glow. The galaxy does not seek equilibrium in stillness. It finds it through motion shared across scales. Every component participates. Stars, gas, dust, fields. Nothing directs the whole. No center commands the outskirts. Order arises from interaction rather than instruction. As epochs pass, the galaxy remains recognizable, not because it resists change, but because change follows familiar pathways. Patterns repeat with variation. Processes echo earlier ones without exact duplication. What exists now carries the imprint of what came before, reshaped by time rather than replaced by it. The Milky Way continues as a slow conversation between matter and motion, uninterrupted, unhurried, and ongoing. And in this continuity, nothing needs to conclude. The Milky Way does not need attention to remain vast. It continues in silence. Stars move, dust drifts. Light travels on paths too long to follow. Nothing here requires effort now. There is no need to remember details or hold on to images. The galaxy can remain where it is, distant and steady, while thought slowly loosens its grip. Breath settles. The space between moments widens. Sound becomes softer. Time stretches without direction. Far above, the slow river of starlight continues, unchanged by observation. It does not hurry. It does not ask. Awareness can drift without destination, like a particle carried by a gentle current. No edge, no task, no signal to follow. Rest does not arrive suddenly. It gathers quietly, the way darkness spreads across the sky without announcement. If wakefulness lingers, it can linger without purpose. If sleep approaches, it can arrive without resistance. Nothing more is needed. Good night.